Today we're going to talk about another type of integration to find volume. And this type of integration is going to use known cross sections. So rather than rotating our curves to create a volume, we're going to be using cross sections that have as their base the distance from the x-axis or from a second curve to another function. And there's going to be a few types of shapes we review. We're going to look at squares, rectangles, isosceles right triangles, equilateral triangles, and semicircles. So first up, we've got this idea of squares. So we know that squares have equal sides, right? So if we create cross sections that are squares, the distance between the curves the distance between the curves here is going to be one side of our square, and the height of that square cross section is going to be the same as that distance, right? Because the sides of a square are equal. The area then is going to be the side length squared. So what we're going to see when we write the area in terms of f and g, g of x, is we've got the area is equal to the side length squared, where the side length is f of x minus g of x. This is going to be our upper and our lower, right? Squared. So now using the integral to talk about that, we're going to be looking at the interval of those cross sections. So if we were to add all of those square cross sections together, that's what the integral is doing, of that area equation. So f of x minus g of x squared dx. We're going to be doing a similar thing with these isosceles right triangles. So remember from geometry, an isosceles triangle has the legs equaling the same length. So that means that this leg is congruent to or the same length as the other leg. That's what makes it isosceles. The right triangle means that the two legs form a right angle. So now when we're considering the upper function of f of x and the lower function of g of x, right? The one leg of our right triangle is the distance between our upper and our lower curve. And then the other leg, which is the same length, that vertical leg, is the same distance. So I've got f of x minus g of x for the distance between the curves, right? And then my vertical leg, since it's an isosceles right triangle, is going to be the same size. So we know that area of a triangle is 1/2 our base times our height, where the height is the piece that forms a right angle with our base. Here I've got a base that's the distance between the upper curve and the lower curve. Oops, that should be minus. Times the height. All right, so remember this is upper and lower. And then that's going to be times our height, which is the one that forms a right angle, and that's the other leg, which is also equal, right? So our area then of one cross section is going to be half of the difference between the curves squared. So when we talk about the volume, we're going to be thinking, okay, we're looking from A to B of half of the distance between that upper curve and that lower curve squared with respect to x. Half is a constant, so we can take that out. Just like when we were doing revolutions, we pulled out the pi, right? It's a property of integrals we can use. And there we have it for isosceles right triangles. Let's think about how rectangles will differ from what we've got going on with square cross sections here. So if you're wondering why all of these graphs are kind of drawn at an angle with our x and our y axes no longer being completely vertical and horizontal, it's because when you draw those cross sections, it's easier to see them when the axis is shifted a little bit. So we can draw the sides as vertical and horizontal and still see those cross sections as the shapes that they are. Anyway, we're looking at rectangles now, which means the length and width, or the base and the height, are not going to be the same. So, whoops. What we've got going on here then is we still have a base that's a difference between our upper and our lower curves, but now we're going to have a height or a width or that is going to be some multiple of that. So I'm just going to write a times f of x minus g of x. So this could be that it's half, right? A could be half the dimension of the base, or it could be 2 times or 3 times. All right, it's going to specify in the problem what the relationship is. So the only difference between a square and a rectangle is there's going to be some distinction, some multiple between the length of the base, the distance between the curves, and the other dimension. It'll give you that in the prompt of the problem, and we'll see that in just a moment. So how does that change my area and my volume equation? Well, my area is my length times my width, or my base times my height. So I'll have f of x minus g of x, my upper minus my lower, right? And then I have that constant in there. So, whoops, that half, if it's half the length of the base, right? Or that 2 if it's twice the length. So we're just going to have a constant out front. That's going to be our scalar that changes it, right, to whatever. Oops, I cannot write today. Changes it to whatever that relationship is. So our volume equation is very much so going to be the same. All right. Just now it's going to have some relationship to the other side. All right, so we've got 2 more types of cross sections to review. All right, and that would be the equilateral triangle and the semicircle. So in equilateral triangle, we're going to need to establish some relationships between the sides and get the height in there so we can figure out the area. So to get the height in there, we need to drop a segment in here that forms a right angle with the base. That would be my height. All right. All of the angles in a right triangle are 60 degrees. So when I draw that perpendicular height there, my value is going to be 30 degrees, or half of that angle at the top. Now we need to relate the sides, all right, to figure out what that height is. So this right here, that piece is half of the difference between the curves, because the height is a perpendicular bisector of that base. And we know that the relationship between the angle across from the 30 and our reference triangle, right, if we've got a 30, 60, 90, which is what we've got here, this is going to be a half of the hypotenuse. Well, let's write it this way. The relationship is like this. All right. So if our side across from the 30 is 2, then the side across from the 60 would be 2 radical 3. So the side across from the 30 here is a half of the difference between the curves. So the height is going to be a half of the difference between the curves times the square root of 3. So the height is a half the difference between the curves. Well, I shouldn't say a half anymore. I should bring that square root 3 out front. So square root 3 over 2 f of x minus g of x is the height of our triangle. So we're going to use that now when we scroll down here and write our area equation. So our area is half the base times the height. So my base is this whole distance here. My height is this length that we just found. So if I do half base times height, I've got half my base, which is f of x minus g of x, times my height, which is square root 3 over 2 f of x minus g of x. So when we simplify that, we're going to have square root 3 over 4 f of x minus g of x squared. So remember, this is upper and lower here. If we were doing them instead with respect to y, we would be doing rightmost minus leftmost, right? Okay, so we've got our area equation. Then our volume is going to be all those areas added together. So from A to B, right? We've got the constant square root 3 over 4, so we can write that on the inside initially, but we're going to take that out in just a moment. The difference between our curves, dx. So we can take out that constant square root 3 over 4. We're looking at A to B of the difference between the curves squared. All right, and now we've got our last type of cross-section to talk about, and that's going to be our semicircle or our half circle. So we've got our entire diameter for the semicircle is going to be the distance between our curves, right? That f of x minus g of x. So when we're talking about area of a circle, so area circle, we know that's pi r squared, right? The area of a semicircle is half of that. So we need to have an expression then, when we go down below and write that area equation, we need to have an expression in terms of our radius, right? So this is just part of the old piece. In terms of our radius. So our radius is half of the diameter. So our radius here is half the difference between the curves. So that's what we're going to be using to substitute in for r. So area of a semicircle equals half pi r squared. So I've got half pi times my radius, 1/2, whoops, times f of x minus g of x. Squared. All right, that's my area. And then if we keep working it down, right, we can apply that square to each thing inside of our parentheses. So I've got half pi times 1/2 squared times f of x minus g of x squared. So 1/2 squared is 1/4 times 1/2 is 1/8. So I've got pi over 8 times the difference of my curves squared. So when we add all those cross sections together, we use our integral. Of the area with respect to x, so with that dx. And then the pi over 8 is a constant, so we can take that guy out front. All right, so that's our notes when we've got, so what we just wrote. So when we're talking about with respect to x, or functions f of x and g of x, all right, this is going to be when our cross sections are perpendicular to the x-axis. By and large, this is going to be the type of problem you get. But let's say instead of them being perpendicular to the x-axis, those cross sections were perpendicular to the y-axis. Well, with respect to x, with respect to y, that would be using the functions f of y and g of y. Right? And this would happen when we have the cross sections perpendicular to the y-axis. Like I said, the first case is going to be what our problems will use for the most part. You very rarely see one that's perpendicular to the y-axis. Pretty much all of them are going to be perpendicular to the x-axis. But were we to do one where it was perpendicular to the y-axis, we need our functions in terms of y. All right. So that concludes our notes for this section. We'll pick up with some practice problems in the next video.